Hello guys! Welcome to the TC7 math tutorial. This day we're gonna be talking about the limits of a function. So first, let me show you some of these graphs. Do you still recall those kinds of graphs? Those are graphs of a function. You have undoubtedly encountered functions in your previous years in mathematics courses, particularly in the advanced algebra. But because they are fundamental in calculus and serve as a unifying concept throughout the lesson, we devote the first part of this lesson to a review of their concepts. So first, let me ask you, what is a function? A function is a relation or a set of ordered pairs of numbers, in which no two distinct ordered pairs have the same first number. The set of all admissible values of x is called the domain, and the set of all values of y is called the range of the function. This is a simple illustration of the concept of what we call functions. In figure 1 and 2, we can see that every element in the domain is paired with exactly one element in the range. Therefore, it is a function. In short, the concept of functions is that there shouldn't be repetitions of values of x. Now, aside from this, we can distinguish the graph if it is a function or not by using a method. This method is what we call the vertical line test. From the graph, you can see that for each x in the domain, there corresponds to only one value of y. To determine if the given graph is a function or not, use the method called the vertical line test. If any vertical line intersects the graph of a relation in only one point, then the graph is a function. So this is how to do it. You're just going to draw vertical lines on the given graph. If the line drawn didn't cross us at 2 points, the graph is a function. On the contrary, if the line drawn crosses more than 1 point of the graph is not a function. Just like this. Now, since we had already a short review of the concept of a function, we will go now to our very topic, the limits of a function. Let me start this with a definition of the limits of a function. Let f be a function defined in every number in some open interval containing a, except possibly at the number a itself. The limit of f of x as x approaches a is L, written as: if the following statement is true, given any epsilon greater than 0, however small, there exists a delta greater than 0, such that if 0 is less than the absolute value of the difference of x and a is less than delta, then the absolute value of the difference of f of x and L is less than the epsilon. To compute limits by easier methods other than using a definition, theorems have been employed, whose proofs are based on a definition. We call this the limit theorems. These are the following. Theorem 1. Limit of a linear function. The limit of mx plus b as x approaches to a is equal to ma plus b. The limit of 2x plus 1 as x approaches to 3 is equal to 2 times 3 plus 1 is equal to 6 plus 1 is equal to 7. So therefore, the limit of 2x plus 1 as x approaches to 3 is equal to 7. Theorem 2. Limit of a constant. The limit of c as x approaches to a is equal to c. The limit of 5 as x approaches to 2 is equal to 5. Theorem 3. Limit of the identity function. The limit of x as x approaches to a is equal to a. The limit of x as x approaches to 3 is equal to 3. Theorem 4. Limit of the sum and difference of two functions. The limit of f of x plus minus g of x as x approaches to a is equal to L plus minus m. The limit of quantity 2 x plus 1 plus quantity 4 x plus 3 as x approaches to 1 is equal to 2 times 1 plus 1 plus 4 times 1 plus 3 is equal to 2 plus 1 plus 4 plus 3 is equal to 10. Therefore, the limit of quantity 2x plus 1 plus quantity 4x plus 3 as x approaches to 1 is equal to 10. Theorem 5. The limit of the product of two functions. The limit of the product of f of x and g of x is equal to L plus m. 5. The limit of x times 2x plus 3 as x approaches to is equal to the limit of x as x approaches to 2 times the limit of 2x plus 3 as x approaches to 2 is equal to 2 times 2 times 2 plus 3 is equal to 2 times 4 plus 3 is equal to 14. So therefore, the limit of x times 2x plus 3 as x approaches to 2 is equal to 14. Theorem 6. The limit of the nth power of a function. The limit of f of x raised to the power of n as x approaches to a is equal to L to the power of n. The limit of quantity 5x plus 7 raised to the power of 4 as x approaches to negative 2 is equal to the quantity limit of 5x plus 7 as x approaches to negative 2 raised to the power of 4 is equal to quantity 5 times negative 2 plus 7 raised to the power of 4 is equal to negative 3 raised to the power of 4 is equal to 81. So therefore, the limit of quantity 5x plus 7 raised to the power of 4 as x approaches to negative 2 is equal to 81. Theorem 7. The limit of the quotient of two functions. The limit of the quotient of f of x and g of x as x approaches to a is equal to the quotient of L and m. Theorem 7. The limit of the quotient of x and negative 4x plus 3 as x approaches to 2 is equal to the quotient of the limit of x as x approaches to 2 and the limit of negative 4x plus 3 as x approaches to 2 is equal to 2 over negative 5 is equal to negative 2 over 5. So therefore, the limit of the quotient of x and negative 4x plus 3 as x approaches to 2 is equal to negative 2 over 5. Theorem 8. The limit of the nth root of the function. The limit of the nth root of f of x as x approaches to a is equal to the nth root of L. The limit of the third root of x as x approaches to 8 is equal to the third root of 8 is equal to 2. So therefore, the limit of the third root of x as x approaches to 8 is equal to 2.